Good morning, everybody. Good morning. I'm not ready. Are you? Still have the Physics 2A binder up. Last semester, I didn't have to switch topics. I just went right back into the same thing. So if I start teaching about kinematics, you guys know something has gone absolutely wrong. I want you to turn to each other and start making a list. Tell your people next to you everything you know about electrical charge. Go. All right, what'd you come up with? It's zappy. What do you know about charge? Oh, it comes in 2 flavors, right? Vanilla and chocolate, strawberry and raspberry, positive and negative. It's just a label. It's just a label. Okay, so it comes in 2 flavors. What else? That it? Oh, come on, you know what happens when opposites attract? Whoa! What are we talking about now? It's not dating advice. Opposite what? Signs, opposite flavors, right? Like to do what? Attract. What is that? What is that? Put your Physics 2A hats on. Force! Right? What's a push or a pull? What's an attraction or a repulsion? It's a force, right? So do forces exist between electrical charges? Yes, they do. Okay? In addition to being different flavors and having opposites attract and likes repel, we also know that charge is fundamental. Now, when a physicist says that, what we mean is it's a property of everything in the universe. Everything has charge, okay? Except for the one thing that doesn't. What's the one thing that doesn't? Also doesn't have mass. Light. More on that later. Second half of the semester. Okay. So, this desk right here, does it have any charge? It does. It's full of positive and negative charges, electrons and protons and all that kind of stuff, right? But overall, we say it's neutral. And when we say it's neutral, what do we mean? There's a balance of charge, right? There's not an absence of charge. There's a balance of charge. And so when we say that charge is fundamental, it is a key part of what makes our universe our universe. Like mass, charge. All right. This is one too many cats that did their business in my kid's sandbox. No. This is an ethically sourced rabbit, whatever that means. That's what it said in the cat book, okay? And this is a piece of rubber, okay? I'm going to rub the fur, the rubber rod. I'm going to bring it close to this thing called an electroscope. What do you think an electroscope does? Detects electricity, okay? Detects the presence of charge to see what happens. So I rub the fur on the rubber rod. Oh! You're welcome. Okay, right? So the needle deflected there, right? Okay? Why did the needle deflect? I mean, I touched it with a charged object. How did I get the charges to appear? Friction. I rubbed two things together, okay? And I obviously deposited something on there, and those somethings are repelling each other, right? So, what was the something I put on there? Was it positive or negative? That was quick. This is a glass rod, and this is a piece of silk, okay? I'm going to remove the excess charge from my electroscope, okay? I am magic, I can do that. And I am going to rub the silk on the glass rod here, and I am going to touch the electroscope, and you can see the same thing happen, right? Now, if you were really observant, you'd see that that's a little bit weaker, okay? The transfer charge isn't as effective between silk and glass, but let's see if we can, okay, so I deposit a little bit more there. You can see the needle's deflecting more right after I put more on there. It's much easier to get this to work than it is to get that to work. But if I come over here now, and I rub the rubber rod, and I touch the electroscope with it, it was hard to see, but what did the needle do? Is it deflecting as far as it was before? No. So in putting the glass rod's excess charge on there, the needle deflected. And then when I touched it with this one, it came back a little bit. What does that tell you? They're opposites, aren't they? But which is which? Which one's positive and which one's negative? How do you know? You don't. What matters is that they're different, okay? What matters is that they are opposites and they can cancel each other out. But the label that we attach to it, positive or negative, is entirely arbitrary and was chosen for you by none other than Benjamin Franklin. Benjamin Franklin, yes, the guy that flew a kite in a lightning storm, who, no, did not hold on to said kite string during a lightning storm because he was smarter than that. He decided which one was positive and negative. He had a 50-50 chance and he got it wrong. Because when he said that the rubber rod was charged negatively and the glass rod was charged positively, he didn't know it, but at the time, he would set the sign for the charge on the electron. Why are electrons negatively charged? Ben Franklin chose wrong. And why did he choose wrong? How many of you screwed up a minus sign on an electron or an ionized atom or anything like that? It's a pain in the neck. You can blame him. You can also blame him for time zones and daylight savings time. When I get to the other side, I've got a bone to pick. He did some amazing things. He was genius, a really amazing statesman, and by all accounts, a decent person. But man, when you are sitting there late at night and you can't get Wiley Plus to accept the answer, and you put in a minus sign and it works, that's Ben Franklin's fault. Don't come after me. That's Ben Franklin's fault. Okay, so you saw that I was able to transfer charge to the electroscope by touching it, right? I actually took the rod and I touched the top of the electroscope. This part right here is connected to all these parts down here. The outside is just a support structure and is actually insulated from everything else. So there's a conductor that exists between this plate and the rest of the device. A conductor means something that lets electrical charge move through it. An insulator is something that prevents the motion of electrical charge. Can insulators be charged? Yes. They're actually really, really good at being charged, as I just demonstrated. What is rubber, a conductor or an insulator? It's an insulator. And I can charge it up. As a matter of fact, what's this? It's a water balloon. Don't have any water in it. It's got air in it, right? Okay. What's it made of? Rubber, latex rubber, right? Okay. What just happened? I rubbed the balloon on my head. Magic physics hair. No, this works on your hair too. The rubbing caused a separation of charge. Whatever charge ended up on the balloon, let's call it negative. Okay? Why are the negative charges on the balloon attracted to the charges in the wall? What does the wall have in it? Positive and negative. It starts neutral, doesn't it? But the excess negative charge on the balloon is attracting the positive charges in the wall, and opposites attract, and it'll stay there. Ashley, let me know what fall.
Okay.
Ready to do? You don't have to.
I'll wait.
Don't pay attention to it. No, I distracted Ashley. I shouldn't do that. Okay. But watch this. I love this stuff. So cool. I don't have to touch it. It's Wi-Fi built in. What is going on here? This thing is negatively charged, right? According to Ben Franklin. Okay. What does that mean this thing is? It's got to be positive, right? We started neutral. We have to end with neutral. Charge is fundamental. It can neither be created nor destroyed. You can move it about. And when I say something is negatively charged, what I mean is that there are excess negative charges on it. Right? When something's positively charged, what do I mean? There's positive, excess positive charges on it. Right? It's no longer neutral. But you saw here that I was able to take this negatively charged object, just hold it near the electroscope that's made of conductors. Does the electroscope have charges in it? Yes. And what do the positive charges that are in the electroscope want to do with the negative charges on the rubber rod? They want to get as close as possible. And so the positive charges will rush up to this top plate right here, leaving the negative charges behind. And what do a bunch of negative charges want to do? Get as far away from each other as possible? And so they will. The nature of charge is absolutely fundamental to our understanding of how the universe works. What I've demonstrated here for you is that there's two kinds, that they can cancel each other out, and that we can influence and polarize different things. The wall is polarized right now. It started neutral, but we convinced it to be slightly one way or the other because of the presence of another charged object. I polarized the electroscope by bringing this charged object next to it. I can transfer the charge. I talked about conductors and insulators. But we can fool around with charge, and charge will manifest itself as we do so. Okay, so with all of that, let's see how well you are doing. No, it's coming. You ready to take 3? I probably didn't give enough right there. 3 for now. I'm probably not handing that up here. If we run out, let me know. You do your quiz sheets, all right? If you haven't had me before, hold on for the ride. Somebody near you will help you. Yeah, I see. I didn't have to open it. So somebody else, did I miss anything? Quizzes are back. All right. Remember, they come in 2s, right? And what are you going to do for the first one? Answer it with who? Just yourself, right? Do your best. Answer it yourself. Okay? And then we'll lock it in stone, and then we'll move on to the second one where we get to talk about everybody else, right? Okay? 18.1, 8.2. 2 points for both of those, and the only difference between them is going to be who you can talk to. Okay? So, oh yeah, this is my demo. Blah, blah, blah. Fill out your quiz sheet. And don't forget to put down reasons. Okay. Here, whoops, is your quiz question. .2 points. For the purposes of this problem, assume that the cat is positively charged after it runs down the pole. Oh, I said that in the problem. Good for me. To be clear, you should have 3 answers, right? The charge on pail A, the charge on pail B, the charge on pail C. I'm going to give you 30 more seconds. And then we'll put you out of your misery. All right. Hopefully you figured out what the charges were and that helped you to answer which of those answers was correct. Okay? So what I want you to do now is turn to each other and see if you can't figure it out. So I'm guessing most of you are very confused.
Oh, wait. Because, like, I don't feel like it's right. After some break, everything. So I would assume that the A and B are connected. Right? The A, I'm assuming A is negative. And C is positive. So to explain why A and B are connected to each other. So if everything breaks, I feel like everything. I'm gonna put your answer though just in case. No. Like, it doesn't matter. Your chances are higher if you send me the answer. Because I feel like both of them make sense.
All right. I'm going to send around this is the official roll sheet, right? Just check here, check your name off. I know the dates are wrong on the top. Just do the Wednesday or the Tuesday line. All right. So I'm just going to answer this one for you rather than torture you with it. Okay. But let's see how you're doing. Okay. So the cat comes off positive and hits pail A, which is a conductor. Right. So what does that mean the charge is on pail A? It's positively charged. Transfers the charge. Just like I used the rod to transfer to this conductor, right? The charge on the cat transfers to pail A, right? Now there's charge on pail A. What are the charges on pails B and C? They are neutral, right? Meaning a balance of charge. But now there's a bunch of charge on pail A. And what is that charge on pail A going to cause to happen on pails B and C? What's the balloon doing? What did my rod do? It caused a polarization, didn't it? So that means since B and C are both conductors, meaning the charges can move, and they're in contact with each other, all of the negative charges on B and C are going to pile up as close to the positive charge on pail A as they can. And where are the positive charges on B and C going to try to go? Away. They're going to try and get as far away as possible. Now the shelf breaks. Everything hits the floor, but the floor is an insulator, so no charge can be, right? It's an insulating shelf. So no charge, right? Okay. So what do the pails end up as? What's the charge on pail A? Positive by conduction, by actual contact with the charges. Okay. And then pails B and C. B has what? Negative charge. C has positive charge. We call that induced charge. Something didn't actually touch those pails. They were induced, they were polarized and forced, and then they were separated. And so now the charge can't get back, right? And so we induce the charge. We're going to be doing this in lab, not this coming Monday, but the Monday after. Okay, you'll be playing around with induced charges and measuring charge and all that kind of stuff, right? And yes, this question is probably a little bit unfair, right? Because there's a lot of stuff going on in this question, but it does hopefully help to pull together a little bit some of those concepts about charge that we talked about. Insulators, conductors, how to charge something, the fact that charges are opposite, that neutral things are not zero charge, they're a net charge of zero, and all those kinds of things. So, based on this, what should the answer be? B. And who grades you? You do. 100 credits. We're going to meet a lot of old white people this semester, okay? And a lot of them are going to have like French names. Balogh. So, I've got to come clean. I lied to you a lot last semester. You know? But do you know the depth of the lie? Yeah. So, let me tell you what Coulomb's law is, and then I'll tell you how I lie. Coulomb's law, whoops, it's not that, come back. Coulomb's law is the mathematical description of the force that exists between charged particles. It consists of a constant. We're going to use the letter K. Do you remember K from Physics 2A? It was a spring constant, it was a wave number, it was something, right? K. Remember, context is important. This constant, I'm going to use K sub E just to like really hammer home. I think your book just uses K to hammer home that this is the electric force constant. It's a constant times two charges, the product of two charges. Those are little q's, sometimes capital Q's, but I like to use little q's. And then the distance between them squared. Okay, so first of all, this is a force, and I've given you the magnitude of that force based on some numbers that we'll talk about here in a second. A force is a what? Vector, scalar, or elephant? Force is a vector, isn't it? So it has direction. And that direction is set by that rule of opposites attract, likes repel. This looks like something we talked about in Physics 2A. There was a force that we ended up studying the second half of the semester that involved a constant and two things interacting and a distance between them squared in the denominator. Gravity. Do you remember that one? Trying not to. It was big G, M1, M2 all over R squared. Now, what was the funny thing about big G? It's an oxymoron, big G. It's a really tiny number, if you remember. 6.67 times 10 to the minus 11, whatever units, right? It's a really, really tiny number. And gravity just feels so strong because we're near a massive planet. The electric force constant is 8.99 times 10 to the 9 Newton times a meter squared divided by a Coulomb squared. The Coulomb is the unit, the SI unit of electrical charge. What kind of number is that constant right there? It's a big number. That is 8.99 billion things. Which one's stronger? Gravity or the electric force law, Coulomb's law? Bet up till now you believe that gravity was stronger. So let's do an experiment. Right, it's science, we can prove it, okay? We're gonna go out to the stairs right here and I'm gonna throw you over one at a time, okay? As you approach the ground, I want you to take some notes, okay? And this is the thing I want you to try to observe. Which is stronger? The force of gravity acting on you, or the force of repulsion between the charges in your body and the charges in the ground? Which one's stronger? Who wins? Gravity or Coulomb's law? If gravity won, what would happen as you approached the ground and interacted with it? It would get out of the way. The force of repulsion between the charges in the ground and the charges in your body wins and stops gravity. I'm stopping gravity right, well, not me. The floor is stopping gravity right now. The force on me is approximately 167 pounds. What's the electric force law acting on me right now? Clue, my acceleration is 0. If gravity's pulling down on me with 167 pounds of force, what's holding me up? What did we call it in Physics 2A? The normal force. What the heck is the normal force? It's Coulomb's law. We never said it. The force exists in perpendicular surface of contact. That's all true. But it was a cover-up. It was a cover-up for the most fundamental force that you experience every single day. Now, you experience gravity every single day. I get it. But that just pulls you down, right? Makes it hard for you to get up in the morning, all that kind of stuff, right? Coulomb's law. This description of the fundamental interaction between charges in our universe are responsible for how atoms work, for how your eyeballs can gather photons, how the nerve impulses from your fingers and brains and toes and everywhere else can get into your brain. It's responsible for the fact that your rear end is not sliding through the seat right now. Notwithstanding these are Fresno City College, all the chairs are broken. Touch your fingers together. Just do it. How do you know that the touch is happening? Coulomb's law. Coulomb's law. The atoms in your fingers don't want to be together. The positively charged protons will not. Coulomb's law. What's tension? Where does tension come from? The string. It's Coulomb's law. It's that act of attraction that's tying the atoms together, those electrical forces that hold the material together. What's friction? It's Coulomb's law. It's all Coulomb's law. There are 4 fundamental forces in this universe that we know of. They are gravity, Coulomb's law, the strong nuclear force, and the weak nuclear force. The strong nuclear force is responsible for holding atomic nuclei together. We'll get there at the very end of the semester. The weak nuclear force mediates radioactive decay. We'll get that at the end of the semester. You spent all of last semester working with Coulomb's law and you didn't know. So, this semester we begin by diving deep. Deep into the fundamental force that governs everything. Everything. And it, what does this mean? All right. I got a little video for you. It's cute.
Electricity attracts when it acts between charges of different signs. But acting between charges that are the same, it repels. According to Coulomb's law,
the force 2 charges exert on a third is the vector sum of the forces each alone would exert. In fact, the forces from any number of positive charges and negative charges add together as vectors. So the total force is still calculated from Coulomb's law. Notice that positive charges are shown in red and negative charges are shown in blue.
Yeah, Ashton's awake now. You all right? Don't panic! Don't panic! Okay, first of all, number one, did you see that it was 3D? Right, beyond the creepy cut-off hand thing that was floating around. Right? Oh, did you like the really trippy music? Okay, so you saw that it was a three-dimensional thing, right? Okay? Don't panic yet. We're doing 2 dimensions for now. We'll get to 3 dimensions. Mathematically, okay, so this is Coulomb's law right here, because there's a force, there's the electric force constant, the charges, and the distance, right? Okay? What's this? Sum. We have to add together, okay, all of the forces that are acting on a charge, right? So the desk, my hat, everything has got trillions upon trillions upon trillions of charges in it. And a single charge in this structure is going to experience a force from all those other charges around it, right? So we've got to go through, we've got to add up all of those things, okay? So that means that we need to, well, because it's a force, and because we're going to be adding it together, we need to do vectors, okay? So what I want to do, I want to see if you're grasping the idea of Coulomb's law and vectors and everything together. Let's do another quiz. I know, this seems like these are coming fast and furious, right? Okay? It's important, right, that we kind of nail some of these things. Now, the first quiz and this quiz have both been recorded. Okay? Normally I don't record the quizzes, usually I hit pause. But I wanted these first 2 to be recorded so that go back and review, because I know you're drinking from a fire hose right now. Okay? But let's just check and see, right, how well you're gathering information here. Ideally, you should have been able to do the cat problem after reading the book. Okay? That was my expectation there. This one, between reading the book and what we just talked about, okay, you also should be able to do. By way of explanation, there are 5 choices. One of these diagrams is correct. Note, both of them are positively charged. It's just one has more charge than the other. Thirty seconds. Okay, pick something if you haven't yet. Even if you're guessing, turn to your neighbors and tell them what you think is the correct answer. and y. All right, don't forget to record any changes to your answer for the second quiz. How many of you say the answer is A? Raise your hand. One person, two people? Okay. B? Come on, yeah, B! All right. C? Okay, D and E. Okay, E. Since you were in the majority, we'll make you defend your position. Why did you say the answer was E? Somebody. Don't be afraid to be wrong. Here.
I just thought of like magnets.
Okay.
I was thinking like if you have a really big magnet and you have a smaller magnet, the smaller magnet will repel much stronger than the bigger one.
And this is repulsion, right?
Yeah.
Okay. So why didn't you pick B?
Because I was thinking the more positive charged sphere.
Because the vectors are wrong?
Yeah.
Kind of thing? Okay. Everybody that picked E is wrong. There are only two people in this room who are right. Because only two people put their hands up for D. Why is it D? Do I need to make you sing the song? You forgot, didn't you? We're dealing with forces, aren't we? And when two objects interact, the forces between them are equal and opposite. How easy it is to lead you into traps. Right? Why did I do that? I wanted to help you remember. I want to pull this Band-Aid off as fast as possible, right? Okay? We can't forget Newton's laws and the nature of forces, because we are dealing with forces here, aren't we? So when two objects interact, even if the charges are different, what must the force between them be? Equal and opposite, right? So it doesn't matter what the mass of the desk or me is. When we interact, the forces between us are equal and opposite. And so there's only one answer here that satisfies that condition, and that's D. Physics is hard, isn't it? And Mr. Bale is mean, isn't he? But now you're not going to forget. You're not. What fresh hell is this? Okay. Little q is a symbol for what? Charge. So here we've got three charges that have been placed on an XY coordinate system, okay? They've told us what the charges are. And since you did yesterday's lab, you now know when I write that, it means what? What's that symbol? What does it mean? Micro. Okay? So that's a microcoulomb right there. Okay? So Q1 is 2 times 10 to the negative 6 coulombs. Q2 is negative 4 times 10 to the minus 6 coulombs, and Q3 is negative 6 times 10 to the minus 6 coulombs. You always want to work in the SI units of your thing. And the SI unit for charge is coulombs. And so if they give you microcoulombs, make sure that when you're doing your calculations that you put the number in 10 to the minus 6. They give you nanocoulombs, 10 to the minus 9, right? Don't enter in 2 into the equation and expect to get it right. Because the electric force constant is written in standard SI units. Standard units in equals standard units out. All right. We want to know the total force on this charge right there, Q2. Q2 is experiencing a force because there are other charges near it. In fact, how many forces is charge 2 experiencing? 2. What are those forces? The force from charge 1 pushing on it, and the force from charge 3 pushing or pulling on it. So, first step in conquering any problem, from physics to chemistry to taxes, is to do what? Visualize, right? Organize your information, draw a picture, do something. Since we're talking about forces, we need probably something that's free body diagram-ish. Forces, vectors, arrows, things like that, right? So, we got to ask ourselves the question, okay, we know Q2 is experiencing a force from charge 1 and charge 2. Which way are they pointing? Well, what do we know? Charge 2 is a negative charge, isn't it? What's charge 1? Positive charge. And what's charge 3? Also negative charge. Okay, so if we isolate, if we don't look at charge 3, because a force exists between 2 things, right? 2 objects. So we can ignore charge 3 and just look at 1 and 2. If we just look at the force between charge 1 and 2, which way is that force pointing? They are opposite charges. Towards each other, right? And so from the point of view of charge 2, the towards each other direction is that way, isn't it? It's along this line that connects those 2 charges. Now, is there a force that acts on charge 1 going up this way? Yes, but we're not worried about, they didn't ask for charge 1, right? They asked for the force on charge 2. So I want to draw forces that are acting on charge 2. So we got that force of attraction, right? Between charge 1 and charge 2. Okay, what is the force doing between charge 2 and charge 3? Repelling. So that's not going down a mountain. That was a funny joke. Too late. No, you guys didn't laugh. I'll take it out against you on the exam. You laughed that time, I wasn't. No, I was joking. So there's that force of repulsion, right? It acts directly away from that other charge. I'm kind of like drawing that dotted line, right? You got to give me some direction to go. Okay, so if we call this, I don't remember how your book does it. I think your book does it. This is the force. Yes. Force on charge 2 because of charge 1, F21. The way your book does it is the little subscript. The first number is the thing that's experiencing the force, and the second subscript is what's causing it, right? So I want to say the force on charge 2 because of charge 1, it's pointing down like that, and then the force on charge 2 because of charge 3. Just to keep them different. They're different from each other, right? So I got to keep them. Okay. So I've visualized here. Okay. I've kind of drawn a picture. The coordinate system is kind of set for me in this problem. I mean, there's sort of like a standard XY thing going on here, isn't there? Because they've given me distances along an XY axis. So I'm just going to go ahead and just keep it X and Y. There's no acceleration here, so we don't have to worry about rotating and doing anything weird like that. We just want to know total force acting on charge 2. So, as a strategy, as a plan, we are going to find the total force acting on charge 2. And we're going to find it by finding F21, and it's a vector, and adding it to F23, which is also a vector. So my plan is, find out what F21 is, both magnitude and direction. Find out what F23 is, both magnitude and direction. And when I've got those two vectors, I'm going to add them together and see what I get. Now we got to do it. How are we going to do it? All right. So let's do F21 first. The magnitude of, can you guys see the green okay? All right. So F21, the magnitude, the number, the strength of this force is going to be the electric force constant times Q2 Q1. I just took my subscripts from the force, right? And I know that those are the charges that are going to be involved. And then I need to know the distance between them. So we should probably go and figure out what the distance between those two charges is, okay? R21 is this entire distance along that diagonal right there. Got a triangle, don't I? Right triangle. Both have lengths of 1 meter on the sides. So what's the length of the hypotenuse? It's root 2. If you did, it's a 45-45 right triangle, right? And so it's always 1 square root of 2 relationship. If it wasn't that kind of triangle and you just had some arbitrary angles in there, you'd have to use trig to find out the length of the hypotenuse, or Pythagorean theorem to find out the length of the hypotenuse, okay? But either way, this is root 2 right here, okay? So that means we can go ahead and calculate this, right? This is 8.99 times 10 to the 9. And I'm not going to put units in because I'm going to put everything in standard units, meaning everything's going to go, if it's a coulomb, it's going to go in as a coulomb. If it's a meter, it's going to go in as a meter, right? I'm going to use the standard units, and that means I'm going to get standard units out. And since I'm solving for force, the standard unit of a force is newtons. So I don't have to use my units. Okay, so Q2. Okay, what is the charge on 2? It's negative, isn't it? But we're not going to put the negative sign in. This is a magnitude calculation. Does magnitude worry about signs? No. When did we figure out the direction of these forces? When we drew the picture, right? Okay? We're just looking for its magnitude. So don't put negative signs in when you're doing magnitude calculations. If you go watch YouTube, people do this different ways, and I'm doing it the way your book does it. Okay? So I'm going to write 4 times 10 to the minus 6. I'm going to multiply that times 2 times 10 to the minus 6. Again, the magnitudes of the charges in there. And then my distance down here is going to be the square root of 2 squared. This is plug and chug, right? I'm tossing in the things that they've given me and that I've discovered from my visualization to figure out what the magnitude of this force is. So I got 0.036 newtons. Now, is your TI calculator going to eat you alive? Yes. Be careful with those parentheses, right? Just be careful. So there's the magnitude of force 2-1, okay? I need to make it a vector. I need to give it a direction, don't I? What direction is it pointed? It's down that way. But what angle is that? What's the angle right in there? Okay, 225 all the way around, but the angle down there is a 45-degree angle, isn't it? Okay, so we know that this is a 45-degree angle. So can we use that to find the components of this vector? Yeah, right? Because f21x is going to be 0.036. And now do I do sine or cosine of 45? Is the x component, right? So I'll draw it down here. This is 0.036 and it points that way and that way. And here's my 45-degree angle right there. Touching or not touching? Not touching, sine 45. F21y, 0.036, cosine 45. Don't forget their directions. What direction is the x component pointing? Negative. What direction is the y component pointing? Negative. And these turn out to be numbers. Negative 0.025 and negative 0.025. How did that happen? 45-degree angle. Sine, cosine doesn't matter. They're the same values. Okay, so there's F21. Go back to the plan up there in red. What's the other thing we need? How are we going to get F23? Same way. We're going to go ahead and take our magnitude. F23 is going to be K Q2 Q3 over the distance squared. That's 8.99 times 10 to the 9. Charge 2, not putting in the sign, just the magnitude. 4 times 10 minus 6, and 6 times 10 to the minus 6, all over the square root of 2 squared. And I'm going to get 0.108 newtons. That's the magnitude. Okay. Again, it looks like this thing is pointed at a 45-degree angle, isn't it? There's a 45 sitting in right there. So F23x, pointing in the negative direction, is going to be 0.108. And then cosine 45, whatever that turns out to be, F23y, pointing in the positive direction, 108, sine 45, gets me negative 0.076 and positive 0.076. Okay, now that I've got the x and y components for both, what do I have to do to get the total? Add x's to x's and y's to y's. Come
I'm confused.
So Mike.
For F21, we got 0.036, but then for F23, we got 0.108. But we do the same thing.
But they're different charges. 4 microcoulombs, 6 microcoulombs. The other one was 4 microcoulombs and 2 microcoulombs. Yes, no? Okay to be confused, where are you confused?
What are you saying to? Or like, where do you?
For the green, it's between this one and this one,
Yes.
right? This one is 2 and that one is 4. But for the blue, it's between this one and this one. That one's 4 and this one is 6. So this force up here I expect to be stronger because there's more charge involved, right? And this one I expect to be smaller, and that's what happened, right? 0.036, and this one's bigger. So yeah, it's different charges, so it's different magnitudes of forces. Excellent question. How are we doing? Your life has descended, it's in tatters, right? Okay, this stuff's hard. It gets really hard at the beginning, and then it's going to get a little bit better. A little bit, and then it'll get a lot better. And then it's going to get really hard again. Okay, but we are working with the fundamental force of the universe here, so we expect it to be a little bit difficult. As a side note, since we're on a slight tangent here, this is only 2 charges acting on a third. How many charges are in that desk? How many charges are in your pen? How many times do you have to add vectors together if you've got a big object that's full of lots and lots of atoms? Trillions upon trillions upon trillions of vectors. We have a trick for that in physics. It's called calculus. What is an integral? It's a fancy way of adding a lot of things up. Are there integrals hiding here? It's about as hard as it gets for you. The 4B students, they come into 4B and we just basically hit them with a 2x4. Like they walk out of the first class concussed because they have seen calculus that has made their hair turn white. Like literally, if you see a 4B student wandering down there, you'll be able to tell because they're moaning and crying, and when you ask them what's wrong, they'll just say something about the electric field. Okay? Just whisper in their ear, it's okay. Integrals are okay, and then they'll collapse a little bit. Where was I? Oh, add all this stuff together. I can't remember how to add all this stuff together. Let's see, I'm running out of room here, so don't worry. Worry. It's still there, okay? I'm gonna go here. Okay, so that means that if I'm gonna put this total together, right, to get the x, I'm gonna do the x component, which was negative 0.025, plus the y component, which is negative 0.076, to get negative 0.101 newtons. And then for the total y component, I do the y components, negative 0.025 plus 0.076. Pretty sure I got all those right. And that gets me 0.051. And now that I've got the x and the y components of these things, so it's telling me it points in the x and the positive y a little bit, right? So let's go back to my picture over there. I had 2 forces. Think of these as like 2 strings, right? Tugging on that charge. One of them's tugging really hard, the other one not so much. So we expect the net force to be kind of off that direction, don't we? And that's what we got from our components here, right? I got a little bit of up, but a lot to the right, left. And so that's what I expect to be happening. The net force of this thing goes this way, right? So it's negative 0.101 going that way, 0.051 going that way. And we need to find out what this force is. If we know the components of that force, how do we find the magnitude of that force? Pythagorean theorem. Square root of 0.101 squared plus 0.051 squared. Are you going to be doing a lot of calculations in this homework? Yes. Am I apologetic? No. Get the angle from the tangent, 0.101. That's going to end up being a negative angle, 26.8. Remember what a negative angle means in the tangent? You're rotating clockwise, right? So what it told me was this angle right here. 26.8 degrees. So the actual angle that it's pointing at is referenced from the y-axis is 153.2 degrees. So there's my magnitude, there's my angle. We were able to find that force. And, you know, there's probably a question that's occurring in your, if you have any brain cells, there's a question that might be occurring, and that is, why would I ever do this? Like, this has nothing to do with filling my major here. And you're not wrong. Like, physicists don't even sit down and do this, right? We have engineers to do it for us. But understanding the fundamental forces that exist between charges is going to allow us to step forward. This is what we want to get to, is an understanding of how neurons work, or an understanding of how electrical impulses are conducted through muscle fibers for physical therapy using a TENS unit. Or maybe we want to know how to control the electrical impulses in an electrical circuit with programming to be able to get a computer or robot or something to do something for us, right? This is where this all starts, right? And so having this understanding is important, and having the problem-solving method down, because we need to move into the next step, which is the electric field. And now, the good news that I have to give you is that this is a step towards simplification and application. What I've just taught you can't really apply directly. There's certain situations where knowing exactly what the charges are doing is important. It's called chemistry. But for the rest of us, how do we handle big collections of charge without having to go to that vector nonsense all the time and figure it out? Well, the answer is the electric field. And your hero is Michael Faraday. Michael Faraday, we're going to talk a lot about him this semester, okay? But Michael Faraday is quite possibly my favorite person in history, okay? Outside of religious context. Scientific history, he is amazing because he's one of us. Not genius. Just stubborn. I'll tell you more about his story later because it's amazing. But Michael Faraday is responsible for giving us an understanding of what I'm about to show you. This is called a Van de Graaff generator. It does not generate Van de Graaff. What it does is have you ever walked across the carpet with your shoes and then touched the doorknob and gotten shot? Have you ever driven your car around on a either very cold or very hot day in Fresno, stepped out of the car and gotten a shot from the door handle? Okay, what do you call that? Static electricity, okay? Static, because the charge builds up and is not in motion, right? It does move from one object to another, but it moves very fast. It's a static discharge. That's different from dynamics, electrodynamics, which we will get into. And any time a physicist put the word dynamic on anything, what do you know? It gets really hard, okay, right? But electrodynamics, everybody else calls magnetism. But what the Van de Graaff generator is it's a static electricity generator. It's the equivalent of rubbing your shoes across the carpet like 10,000 times a minute. Okay? There's a rubber belt inside of here, and there's rubber and felt rollers on the bottom. And as that rubber belt rolls, it's like me rubbing the cat fur on the rod, but really, really fast. Okay? And then it deposits all that excess charge that it's separating out because of the motion. It deposits it on this dome right here. It's plugged in to run the motor, but this wire is not giving any charge to the system. Okay, so any implant? Okay, don't answer that question. All right. See if it's going to work. It was being finicky this morning. Usually goes much faster. I've got to I was doing emergency surgery on this one on Friday because one of the other physicists was demonstrating something with faculty. And when you put English faculty near these things, they tend to break. Oh, there it goes. You see it? Let's see if we can get it. Do you see that? You see that piece right there that's sticking out? Right? Okay? Now watch this. Did you see it respond? You kind of do it over here. Oh. Okay, if I die, tell my wife I love her. Building up a whole lot of charge. Come on. We're leaking charge somewhere, but it is getting some. Okay? What should be happening is this thing should be sticking up a lot. Okay, do you see that piece sticking out right there? Okay, so obviously it's being influenced by a force, isn't it? Okay, and it's being pushed away from the dome. It's like the dome is getting a whole bunch of negative charge on it, and that negative charge is going into the fur, and the fur is being pushed away. But importantly, I can come in here and influence this thing. The electric field is the pattern of forces that exists around any charged object. We didn't talk about it in Physics 2a, but there are things called gravitational fields. The Earth has a gravitational field. What happens when you put an object into the Earth's gravitational field? It experiences a force, right? Okay? What happens when you put a charged object into an electric field? It experiences a force, right? So the electric field, according to Michael Faraday, is the pattern of forces that exists around any charged object. And what we're going to do on Thursday is dive into what that can do to help us deal with trillions upon trillions of charges without having to add up a whole bunch of vectors. We're going to still be adding vectors, because the electric field is a vector. But it's going to simplify what we just did and help us pave a way forward before we can move into circuits. So I'll see you then. Have a great rest of the day and be good tomorrow. Think good thoughts for the Physics 2a students. Their first lab is tomorrow.
I have a video of you doing this at the science show.
Yeah, no, I know. It's just, I gotta replace the belt again. These belts are old and they're not working right.